I find it extremely difficult to imagine that string theory is not in some way connected to the correct quantum gravity theory for our universe. What makes it difficult is that the connection might be quite hard to trace. We have the standard model of particle physics, which describes every experiment we've ever done outside of, cosmology and gravity. And I think there'd be very few people who would argue that what goes on inside a zebra, for example, is in some way in violation of the standard model of particle physics. But that does not mean that we know how to explain the behavior of a zebra, starting from the laws of the standard, the Lagrangian or whatever, the equations that we have for the standard model of particle physics. It's too far removed, and it's much more complex. It's so many layers and levels away from where the theory is simple. We can't bridge that gap. But that doesn't mean we think that the standard model of particle physics is wrong. It's just not, it's too far removed. String theory might be simple at energy scales that I discussed earlier, where you'd have to go like 1 billion times higher than current accelerators, but we can't test it at those scales. And so then to connect the fundamental equations to what we actually see today at the low energies that we can access, well, that's very hard to do, especially if you don't understand the theory completely as we do. And I think we don't understand string theory completely.
Hello, this is Robinson Earhart, here with the introduction to Robinson's podcast, number 216. And this episode is with Raphael Bousso, who is the Chancellor's Chair in Physics at the Berkeley Center for Theoretical Physics. Raphael leads the quite aptly named Bousso Group in research on quantum gravity and quantum information. He's also a renowned string theorist, famous for a number of things, including his development of the string theoretic landscape, which plays a crucial role in fleshing out the string theoretic approach to the multiverse and solving the fine-tuning problem. And then he is also well known for the also aptly named Bousso bound in holography. In this episode, we start off with a historical discussion of the groundbreaking work of many titans in physics, like Gerard at Hooft, Leonard Susskind, Jacob Bekenstein, and Stephen Hawking on the black hole information paradox. Stephen Hawking notably was Raphael's PhD advisor at Cambridge. And after talking about this, we talk about how it led into the formulation of the holographic principle, which roughly states that all of the information contained in a spatial region, like a black hole, for example, is encoded on the surface of that region, which in this case would be the black hole's event horizon. The holographic principle has had pretty major implications for research on quantum gravity, especially for Raphael, who's recently been working on this in connection to quantum information theory, quantum communication, and other ways in which classical gravity knows about, and I say that in air quotes, knows about, and encodes its own quantum states, but you'll hear a lot more about that in our conversation. Reviews, comments, likes, subscribes, as always, these things are tremendously appreciated. There's also a Patreon, a link to which is in the description if you would like show notes to ask questions at the now monthly AMA episodes, or if you'd like a link to an ad-free RSS feed. Now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with Raphael. And when you were at Stanford, were you already interested in quantum gravity by the time you got there, or was that, Leonard Susskind is this huge towering figure at Stanford, and I'm wondering if maybe working with him in part or just being around him sort of shaped you in some way.
Well, it certainly did. I came from Cambridge, UK, where I just finished a PhD with Stephen Hawking. And Stephen, of course, is a pioneer in the field of quantum gravity, maybe one of the most important discoveries in it, that black holes radiate. But for my PhD, that wasn't really a key focus of my research. I was more sort of employed on his cosmology side. He is interested in inflation. Black holes did come into it because he was interested in whether black holes might be produced during cosmological inflation. Cosmological inflation is a hypothetical, almost, I think, very likely theory of what happened very early in the universe when it presumably expanded at an exponential rate for a short period. So I'd come into contact with black holes and some of their quantum properties, but I went to Stanford for my postdoc mostly with a sort of cosmology interest in mind, hoping to work with Andre Linde. And we did work together, which was wonderful. But it's true that I was always interested in quantum gravity as well, and I went to talks that Lenny and his postdocs and students attended and organized, and that drew me into some of their interests, and that's actually when I started working on the relation between quantum information and space-time.
Since so much of your work begins with black holes and holography, and you just mentioned Stephen Hawking's discovery that black holes radiate, maybe that's a good place to start, is with black holes and radiation. So maybe I should ask, why around this time, I mean, before you were working with Stephen Hawking, I think around the 70s or so, why were physicists so interested in black holes, their temperature, their entropy, these sorts of questions?
Well, I wasn't around. Well, technically I was, but I was like 1 year old or something when most of these early discoveries happened. But my impression is, well, people were studying black holes for a number of reasons. I mean, I think it must have been clear that they were objects that were in some ways unique to Einstein's theory of gravity and had no analog in other parts of physics. So it would make sense, I think, to study them if you're trying to understand how to fit gravity in with the rest of physics. Maybe black holes both explain why it's so hard to do that, because they're unique to gravity, but also then perhaps give us a hint for how to do it. I feel as I'm saying this that I'm editorializing a little bit. I mean, this is how it played out. I mean, I think this is what I just said is actually true about black holes. I don't really know whether that hope motivated people working on them at the time. There was a practical, well, by my standards, practical reason, which is that black holes, when they merge with each other or with other compact objects, would emit a huge amount of gravitational waves, and people had started to become interested in detecting such gravitational waves. One of Stephen Hawking's early classic papers, which is now known as the area theorem, it stated that the area of the event horizon for a black hole cannot ever decrease. And the event horizon is sort of the surface that you better not cross if you want to get back out. And it was a theorem of enormous fundamental importance in physics, but the way that he sold it at the time was that it would give him an upper bound on how much energy could be emitted by the merger of two black holes, and therefore, what is the most optimistic amount of gravitational waves that we could hope would be emitted in such a process. So that's one thing that I'm aware of that people were certainly interested in at the time. Another very important foundational paper was by Jacob Bekenstein. And there the famous story is that, his graduate advisor, he was a grad student, his graduate advisor, John Wheeler, asked him, well, it seems weird that we can destroy entropy by throwing it into a black hole. So in physics, one of the most fundamental laws is this second law of thermodynamics, that the entropy cannot decrease. In other words, things become more disordered over time, not more ordered. And one of the most important steps, I think, in understanding the significance of black holes was Wheeler's worry that they could be used to undermine that law.
You said you cannot destroy entropy by throwing it into a black hole. Did you mean information, or are
well, it's
entropy
two sides of a
information?
coin. It's two sides of the same coin. Entropy is sort of the information you don't have. If I give you a single particle, maybe it has something called spin that can point up or down, right? And I don't tell you which of these it is, then as far as you're concerned, it's 50-50. Then you would say this particle has an entropy corresponding to two possibilities that you don't know which one it is. Conversely, I could send you information by giving you this particle, and I'll tell you, well, once you measure the spin, if it's up, it means that the weather is good here, and if it's down, it means that the weather is bad where I am. And so in that same sense, once you learn which it is, then it's information. And a particle might only be able to carry like one bit of information or something. But if I give you a big box of particles, I might be able to send you a lot more information. But again, before you look, if I don't tell you anything about it, then it's just the information that you don't yet have is the entropy.
So the potential information carried by a particle is its potential number of microstates, which is connected to its entropy?
Yeah, we usually take the log of that, the logarithm, to quantify the information or the entropy. But it's very directly related to the number of states it could be in.
And I think I cut you off as you were talking, though, about Bekenstein's crucial contribution at this time.
Yeah, so he was encouraged by Wheeler to worry about something that I think most people would just not have worried about. It's the fact that if you have a black hole, let me first just start with the real world, right? So in the real world, it is certainly possible to decrease the entropy of a system. For example, if I have a glass of water and I put it in the freezer, then when I take it out and it's a frozen block of ice, its entropy will be lower than when I put it in. But the freezer, in the process of freezing this water, will have actually heated up the air in my room by more than enough to allow the air to be in far more states than before. And it will have increased the entropy. And you can check it's going to increase the entropy of the air by more than to make up for the lost entropy of the water when it became ice. It seemed like black holes are like such a fridge, except without the price of heating up the air in the room. That if I instead just throw the glass of water into a black hole, the entropy is just gone, and nothing makes up for it. The reason that was a weird thing to worry about is that most boring people would have said, the entropy is inside the black hole. Just, jump in. And maybe you don't like to go inside black holes, but that's your problem. There it is. It's inside the black hole. Why are you complaining? And yet somehow, I think Wheeler understood two things. He understood, first of all, that if you wait too long before you jump in after the glass of water, you won't be able to reach it even inside the black hole. It will have sort of been destroyed in a singularity and you can't get to it. And he must have also felt that if nobody can verify that the second law still holds, that's really bad. Physical laws should have some operational meaning. You should be able to check that the entropy did not go down. And so if you can't reach this thing, and he was not happy with this. For whatever reason, he had the right sense that this was something to be unhappy about, that most people would have just shrugged off. And so he gave it to his student, Jacob Bekenstein, and said, figure something out. And Bekenstein understood that Hawking had just proven that the area of a black hole event horizon can never decrease. And to a physicist, that immediately reminds you of the second law of thermodynamics. Like there's pretty much nothing else in physics of any fundamental significance that cannot decrease. And so Bekenstein figured, well, maybe what happens if I throw the glass of water into the black hole is, first of all, what's obviously going to happen is the black hole is going to get bigger. Its surface area is going to get bigger. Maybe it's going to get bigger by enough that if I somehow associate black hole entropy to the surface area of a black hole, if I invent this idea, first of all, that black holes have entropy, they have quantum states, and if I secondly propose that that entropy is somehow given by the surface area of a black hole, maybe then it works like putting the glass in the freezer, and and the thing that's analogous to the room in the air in the room getting heated up would be the black hole gets bigger. That's what compensates. The area increases. If I declare that area is entropy, then I might be, I might have a chance of saving the second law of thermodynamics. So he called that the generalized second law of thermodynamics, that the entropy of a black hole plus everything else cannot decrease. Maybe he shouldn't have called it the general. It's just the second law. Once you accept that black holes have entropy, but that was a radical proposal. And it was radical for many reasons. One was that, when we say that the glass of water has an entropy, we have at least some idea of, and in principle we can define exactly what the quantum states are that correspond to all these possibilities. The water molecules can be in different places, they can wiggle in different ways. And we know this because we have some notion of what the microscopic structure of water is. It's made out of molecules. For black holes, there was absolutely no analogous notion. There's no sense of what it's... we still, in general, have no idea what the microscopic states of black holes are. But by this argument, Bekenstein was able to argue that they have some, that black holes are in some sense like things, even though, when you're falling in, it's supposed to be just like empty space, and okay, maybe you get destroyed inside, but it's not, for somebody who falls in, it's not a thing. For somebody far away, apparently it's more like a thing. And it's a thing that can wiggle in different ways. But Bekenstein's proposal was much more, it reached much further than that, because first of all, it was a statement that you can look at a classical property of space-time, and it will tell you how many quantum states there are. Without any further information about what this thing is made of. There's no analog of that in any classical theory of any other force, right? Moreover, gravity not only knows about its own quantum states, but it also must somehow know about the quantum states of matter. Because if Bekenstein's scheme was going to work, well, the black hole has to increase in area by enough to make up for what you're throwing in. How does it even know how many quantum states a glass of water has? Right? How does gravity know that? We actually still don't really know how gravity knows that. It's just that we can check a million examples and it always works. Like it's true that basically you can't. It has to do with the fact that the information content of matter systems seems to be connected in a really deep way with how much energy they have and how big they are. And those last two things are related to how much a black hole will increase in area when you throw the thing in. And a lot of my own work has been on making that relationship more precise and also showing how general it is, that it goes far beyond the realm of black holes and adding objects to black holes, and it really governs. There's a relationship between the area of surfaces anywhere in the universe and the information content of matter systems.
Yeah, so you're pointing directly to where I'm hoping to get to, which is quantum information and holography. And I find it striking that we don't know that much about the microstates of black holes today, given all the advances in holography. But I'd like to get back to that a little later and continue with this black hole dialectic. And you said earlier that Hawking had this very important result that the event horizon of a black hole can never decrease. But of course, this was overturned later. And I'm wondering how this comes after what Bekenstein discovered and then how this relates to the information paradox.
Yeah, that's a great question. And there's a wonderful story that goes with that, which is that when Bekenstein made this proposal, it actually fit quite nicely with some work that Hawking and others had done. I already mentioned the area theorem. Hawking and others had also found that black holes in some other ways behave like thermodynamic objects. They had even identified sort of analogs to all the known laws of thermodynamics. So the area law was sort of supposed to be the analog of the second law of thermodynamics. And there's a first law of thermodynamics which involves the temperature. It relates the increase in entropy to the increase in energy of an object through the temperature. That's sort of what defines the temperature of an object. And they found that black holes satisfy a similar looking law, but they absolutely refused to say, the area law really is a second law for black holes. The temperature that we find in this law really is the temperature of a black hole. Why did they refuse to say this? Or that the entropy is really an entropy? They wanted this to be an analog. Why? Because if a black hole had a temperature, it would have to radiate. Objects that have a temperature, they emit radiation. And everybody knew that black holes are things that just swallow stuff up but don't emit anything, right? So it seemed absurd. Of course, that was it was a mistake to think that way, because that property of black holes that they don't emit anything is a classical property. And what they were implicitly studying were the quantum properties of black holes. But they were very much against taking this analogy, as beautiful as it was and everything fit, too literally. And then Bekenstein came and said, well, I propose for totally different reasons that black holes really have an entropy. And even Bekenstein didn't go far enough to say, well, if black holes have an entropy, then because they have an energy, their mass, they must have a temperature, which we can actually which you can calculate. Right? He could have predicted Hawking radiation just based on that, up to some overall factor that he wouldn't have been able to fix. But the phenomenon as such, he would have been able to predict. Even Bekenstein shied away from that. And meanwhile, Hawking completely dismissed Bekenstein's idea because it couldn't possibly be true that black holes radiate, and he understood that that would be the implication. And then, for totally different reasons, Hawking did a calculation like a year or two later, in which he was trying to understand how much black holes enhance radiation that might come past them when they rotate. There's a sort of classical effect that was known that black holes can sort of give energy to objects that sort of graze them if the black holes rotate and you do the grazing in just the right way. And Hawking decided to calculate what happens to quantum fields, the more fundamental description of matter that we have. And he found that there's some residual radiation that's present even when the black hole doesn't radiate at all. And he immediately understood, so black holes really do radiate. You don't need to send anything in. They send stuff out. And of course, at that point, it became clear that everything really does fit together, and Bekenstein was right, and black holes are these objects with all these real properties, temperature, entropy, that all objects really have. And so, it was a convoluted story. It was like most discoveries in science. It went in a meandering way, maybe, but in the end, it fit together very beautifully.
To put a little bit more meat on the bone, just so people can get a sense of the scale of what's going on here, because I think it's pretty amazing. Just how cold is a black hole? And then maybe how does Hawking radiation occur in a nutshell, and how long does it take?
Okay, so I'm not sure I could give you the exact numbers without going through either looking it up or calculating it again. But to give you some sense, so the radiation that we feel as warmth, like when you turn a radiator on and you stand next to it. So first of all, radiation is like light. It's like the light we see, but it has a bit longer wavelength. So maybe 10 times longer than the light we see. That's called infrared. And the kind of temperatures that we feel when we stand next to a radiator they correspond to these kinds of wavelengths. Now, how big is the wavelength of light? And a few hundred nanometers. So that's like, a 10 millionth of an inch or whatever bizarre units people use in this country. And this light that we can feel as warmth, infrared radiation, has maybe 10 times longer. So it's still, a millionth of an inch or something. It's a very small amount of length that corresponds to the sort of one wavelength of this electromagnetic radiation that we feel as warmth. And the longer the wavelength, the colder it is. Okay, so if you make it 100 times longer than that, you certainly won't feel it as warmth at all. It's supposed to be imperceptible. It'll be very cold. The wavelength of the radiation that's emitted by a black hole is comparable to the size of the black hole. Okay, so if you have, for example, a black hole that was formed by a star collapsing, black holes of that type are maybe a kilometer, a couple of kilometers or miles across. Okay, so the wavelength of the radiation emitted by such a black hole will be a mile. Okay, compare that to the millionth of an inch. So that's how cold it is. It's not a significant amount of energy that's emitted by such a black hole. The black hole itself has a massive amount of energy, as much as the mass of a star. And so for this reason, it takes a stellar mass black hole, even if nothing new were to fall into it, which it does, it would take much longer than the age of the universe.
I think
for it
something
to
like
evaporate.
10 to the 80 years, something crazy like that.
Something ridiculous like that. It depends sensitively on how big you assume the black hole was to start with. The black holes that we believe lie at the center of many galaxies, including the Milky Way, are much bigger than that, yet in length, like a million to 10 billion times bigger. So they would be even colder. Of course, in a realistic environment, they're not losing energy at all because there's matter and radiation present in their neighborhood, and that actually keeps making them even larger than they already are.
So returning back to this story, in entropy or information, something falls into the black hole. Before, it was thought that nothing ever leaves the black hole, but of course, after Hawking radiation was discovered, it turned out that black holes do shrink and something does come out of them. Yeah. How did this result in, or how was this part of the information paradox? And then where did Gerard at Hooft's and Susskind's idea of holography come out of this?
Right. So what Hawking showed at first is that black holes radiate in a way that would look like thermal radiation. Thermal radiation is what you get when you take an object and you put it otherwise in a vacuum, so you have a nice clean situation, and you just heat it up to a certain temperature, and you ask, what spectrum of wavelengths does it emit, and that spectrum will follow a particular law. What Hawking first showed is that the spectrum looked very similar looked that way for black holes. 2 years later, in 1976, he published a paper which went into more detail as to the actual quantum state, the exact quantum state of the radiation that's emitted by the black holes, and showed that it is exactly what is called a thermal state. What's important about that result is that when we say a thermal state, what we really mean by that is we don't know which state it is. It's what's called a mixture of many different quantum states, each with a certain probability. And this is something that, you can easily get. For example, if you have a quantum system and you break it up into two pieces, and I give you one and I take the other, and then even though the whole quantum system might be in what is called a pure state, a very definite quantum state, each of us would say, would not be able to ascribe a definite state to our piece of the system. In fact, it might be completely indefinite. It could be any out of a gazillion different possibilities. It's only when you put it back together that you can recover the pure state. Now, what's not supposed to happen if I put a quantum system, I don't know, a glass of water, into an isolated environment, perfectly isolated, and I just let it sit there, it might evolve. Maybe the glass will even break and the water will spill on the floor or something. But so long as I have it in a box that's completely well isolated, the final quantum state will be a definite one, a pure state, if the initial one was a pure state. And there's some law that tells you the evolution from one to the other. But the important thing is that you can always predict or retrodict. You can go back and forth, just like with classical physics with a cannonball. If you know how fast it's moving now, you can calculate how fast it was moving and where it was at earlier times and where it will be at later times. It's completely deterministic. And this is actually a fairly fundamental principle in quantum mechanics, that if you don't interfere and you've got a well-isolated system, then you should not be able to lose quantum information. You should not be able to go from a definite state to not having a definite state. What Hawking showed is that if you make a black hole, say by collapsing a star in a pure quantum state, very difficult, by the way, to arrange this in practice, but we don't worry about the practicalities here. This is a question of, an in-principle issue with the laws of physics. So you make such a black hole, you know what the quantum state was in the beginning. It was that of a star. Now, you don't know too much about how to describe black holes because we don't have a quantum theory of gravity. Doesn't matter. The black hole is going to evaporate. It's going to return all of its energy to the universe. Eventually, it'll be gone, and all you'll have is a cloud of radiation. That's, precisely the kind of situation like I had this glass of water, and a day later I come back into the well-isolated room, and it's a puddle on the floor. I don't really care what happened in between. One thing I'm going to insist on is that it better be a pure state in the end if it was a pure state in the beginning. That's sort of a basic principle. And what Hawking found is that this Hawking radiation cloud that we're left with at the end is in a mixed state, even if we started in a pure state. That it is, and in fact, it's sort of in the same mixed state no matter how you made the black hole, for so long as the black hole has the same mass to start with, it's going to produce exactly the same mass of Hawking radiation no matter what you made it from. And so this would have fundamentally altered the reversibility and deterministic nature of the laws of quantum mechanics. And it seemed like so how people responded to this depended very much on which community of physicists they were from, strangely. So if you were primarily trained in general relativity and in Einstein's theory of gravity, the theory that tells you how black holes work and what they look like and so on, you were perhaps likely to just shrug your shoulders at this and say, well, duh. The information went into the black hole. Obviously, it's not going to be also outside, right? I mean, what's your problem? Why are you making a fuss about this? If you were a particle physicist who studied, collisions of particles at big accelerators and people discovering new particles all the time this way and so on, and you've been mostly thinking about quantum mechanics all your life, then you would immediately protest this conclusion and say this is completely crazy because even, once you throw out this basic principle of what's called unitarity, that information is not lost. If you throw this out when you consider processes where black holes form and evaporate, you're not going to be able to confine it to those settings. Principles are principles. They either hold or they don't. Once the dam breaks, forget it. And it's very hard to understand why the principle would hold to such a good approximation if it's fundamentally just not true. Yeah, so it was hard, I think, initially for these communities to sort of even understand where each other, were coming from. Stephen himself was certainly in the GR camp, and he was the one who first proposed that information is lost. And people like John Preskill, Lenny, of course, and at Hooft were, found this hard to believe. And I think my own favorite, like if I imagine I had lived I've been part of physics in the 70s and early 80s when these opinions were sort of formed. I'm a little bit surprised that the following argument was never made. Bekenstein had already argued that black holes are like things. They have an entropy. It would be extraordinarily strange if they had an entropy, but they did not store information. The thing that makes you believe that information is lost inside a black hole is the viewpoint where a black hole does not have a consistent thermodynamic description from the outside. It's the viewpoint where, okay, the black hole the information went inside and there's simply no imprint of it. But if I have a box and I throw information in it and the entropy of the box keeps going up, then I have every reason to believe that at a detailed level, if I knew the quantum state of the box, there would be my information. It would not be lost. There was no reason for black holes to obey this second law and to have an entropy if they weren't secretly going to store the information and return it to the exterior. But anyway, that's not the argument that was made. So that's the paradox. The paradox is that Hawking's calculation was very robust. He did not make assumptions that we could easily question. Essentially, the only important assumption that he made in his calculation is that general relativity, Einstein's theory of gravity, is not totally wrong at the horizon of a large black hole. No, large is good here. Large means that space and time are not curved very strongly at the horizon of the black hole. It means that you should be able to trust the theory. We think we can't trust it when they're curved on very short distance scales. Then maybe we need, a quantum theory of gravity. But general relativity should not be totally wrong in settings like this, where it clearly works, where, the curvature of space and time is weak. That's all that Hawking was assuming. And people try to have it sort of both ways for a while. Not question this assumption, but at the same time wanting the information to come out. That was the idea of black hole complementarity that was sort of formalized in the early 90s, again by people like Susskind, Preskill at Hooft, and others, that you get to have your cake and eat it. For an infalling observer, there's nothing special at the horizon of a black hole. Einstein's theory is totally valid. And yet somehow the information comes out. Another very important development came in 2012 through a paper by Ahmed Almeri and his collaborators, now known as the firewall paper. That paper was essentially just saying, well, if you want the information to come back out, you can sort of run that outcome backwards and show that the horizon of a black hole cannot be even remotely, even approximately given by the description that general relativity gives it. There has to be some kind of structure there. It cannot just look like any old piece of empty space, like which is what Einstein's theory says. So it sort of sharpened the conflict. It said you can't have your cake and eat it. You have to choose. You either have to say that information is lost, or you have to say that Einstein's theory is completely wrong in a place where you had every right to expect that it should be an extremely good approximation. And so that was, to me, actually a big shock at the time. So at that point, I'd been in physics a while, and I was certainly sort of vaguely convinced that complementarity made sense. Details remained to be worked out, but but that paper showed that, we had not come close to resolving this issue. And I feel like we still have not resolved this issue. I think what's very likely true is that the information comes out. There's a huge amount of evidence for that. So if you define resolving the black hole information paradox as just answering that question, yes, no, does the information come out? I'd say we can be very confident that has been answered. It comes out. But if you define the black hole information paradox as I think you should, which is as the question of, well, how do you reconcile the information coming out with the description of a black hole according to general relativity? How do you recover general relativity as an appropriately accurate approximation at the horizon of a large black hole? I think that is something we have not resolved. And it remains, to me, a really interesting question.
I have a somewhat speculative question because you can't get into Hawking's mind in the 70s and 80s. But something you said that jumped out at me was Hawking and the other relativists in the general relativity camp kind of shrugged at the possibility that information was lost. And what I find striking about this is you mentioned that this would require giving up unitarity, which is crucial to quantum mechanics. And if that's the case, and I also, if I have my history correct, this was around the time that the standard model was really crystallized. And I'm wondering if that meant that Hawking thought that quantum mechanics really just needed to be revolutionized.
I believe so, yeah. I believe that he thought that, and I don't think that was a silly thing to think. If you're, when I was a high school student, I read a bunch of popular physics books, or I think my aunt gave me a subscription to Scientific American. So occasionally I'd get a little bit of like what people were like worried about in the world of physics, and I got wind of the fact that people wanted to quantize gravity, and so I tried to read a little more about this, and eventually it sort of, I remember that it felt unfair to pick on gravity. So if you have two theories and they're in conflict with each other, in this case Einstein's theory of gravity and the sort of general framework of quantum mechanics that worked so well in the world of particles and subatomic phenomena and so on, and they don't fit together, well, okay, it's clear that at least one of them has to be wrong. But why were we so sure it's not quantum mechanics that's at fault, right? Well, how come everybody is saying, oh, we got to quantize gravity, as if it's gravity that's the problem? We got to make it more like the other, the teacher's pet, quantum mechanics. And so this, I remember asking some famous professor even that I ran into, I think he was Heisenberg's successor. Why is everybody wanting to quantize gravity? Why couldn't it be the other way around? I have no idea what he answered. He was probably like, was this crazy kid? But Hawking had every right to say, look, I have studied an effect that has to do with quantum gravity. It can give us a hint, it can give us some information about what we should expect from a quantum theory of gravity that unifies quantum mechanics and gravity. And the hint is crystal clear. Unitarity is going to have to go. Now, of course, always when you overthrow some theory, you have to explain why it worked so well. So in Hawking's case, he would have to understand eventually why, if unitarity isn't fundamentally true, why it looks like it's true, most of the time. And people came up with arguments why that would be a very hard case to make. But it's not like that has never happened before. Every time we come up with a new theory, when Newton came up with his universal law of gravity, he had to explain why Kepler was essentially right about the orbits of planets. So he had to do a calculation in his new theory to see that comes out as a limiting case, as a special case. When Einstein replaced Newton's theory of gravity with general relativity, he had to do exactly the same thing again. He had to show how Newton's apparent, force law comes out of a theory in which there aren't even any forces, just curvature of space and time and things trying to go as straight as they can. And it is quite miraculous, to see a law that's, formulated even in such completely different language like Newton's force law emerge from these totally different concepts. And it's a beautiful thing, when it works. But that's definitely that's a test. That's the first test of your new theory. It's what, unfortunately, most crackpots who send me emails, don't understand, is that your new theory doesn't just have to explain some esoteric thing that we don't understand the answer to. It also can't just, we can't just give up on everything else that we've already explained. You have to recover all that stuff. And there was, I think, no reason a priori to think that that couldn't happen. So I think from Stephen's point of view, I'm really guessing, I never asked him this, but it would have been very reasonable for someone to say, look, I've discovered that unitarity is not fundamentally true. Information can be lost in nature. It's a quantum gravitational phenomenon. And, when we have the full theory, we'll understand why it looks a lot of the time like it's not lost. That was to be determined.
Parenthetically, I am curious, do you get a lot of emails from people who propose to have solved these major problems like quantum gravity?
Every day, yeah.
Every day?
Oh, yeah.
Any of them particularly exciting?
I wouldn't know anymore. I don't.
You
I don't get past the first line, yeah.
There's a professor at Stanford who I won't name, but he told me that he'll charge people $500 an hour to go over their papers with them. And because we're in the Bay Area, he does get some takers from tech people.
I've heard of that. Yeah, I've heard of that scheme. I guess next time I'm in a pinch, I'll try to remember that. That's good. Yeah, the other method I've heard about is that you put them in touch with each other.
Oh, that's sweet.
And then each will complain to the other. It's a total crackpot, but I don't know. I mean, who has time for this? It's life is short.
Mm-hmm. That's funny. Oh, okay, but returning to our narrative, we left off with this idea of black hole complementarity, which connects to quantum mechanical complementarity. But I'm wondering if black hole complementarity is, or can be thought of as something of a precursor to the holographic principle, or are they connected?
Well, let me give you my understanding of this notion of the holographic principle. I remember back when I was a grad student working on not so much, quantum information and quantum black holes, but in cosmology, there were other students who were working, who were closer to the sort of quantum information side even then. And I remember that this paper came out by Leonard Susskind, The World as a Hologram. And I had absolutely no idea what that was supposed to be about, but I remember people talking about it. Oh, Lenny, very creative.
Very cited.
I don't know, exactly what he means by that. Nobody really knew exactly what he meant by it, I think. Not among the people that I talked to, because it wasn't, I don't think Cambridge at the time was sort of focused on that question. And certainly we were in the camp, I suppose, to the extent that there were camps, I guess. Cambridge must have been in the informationist lost camp, in which case you don't have to worry about this stuff. But yeah, in fact, Lenny's paper was, of course, a seminal paper in the field, and so was a paper by Hooft about a year earlier, which got absolutely no attention because he confusingly entitled it Dimensional Reduction in Quantum Gravity. Dimensional reduction is a term in physics which at that point was very boring and old and nothing interesting. It's that there might be extra dimensions, and that if you formulate your theory in 5 dimensions and one of them is sort of curled up, and that leads to some consequences in the 4-dimensional 3+1 space and time dimensional world that we see. And it's endless numbers of papers on this sort of thing, and it's fine, but at Hooft packaged this paper in a way where it was all, it almost felt like he was deliberately hiding what was in it. I mean, you couldn't have given it a worse title than this, because it totally misled people as to what it was even about. It sounded like it was about that well-studied topic, nothing new. In fact, what he was saying in that paper, and what Lenny, I think, articulated in a way that people found much clearer later on, is that let's just go back to Bekenstein. In fact, Bekenstein has sort of said these things as well. If you want Bekenstein's way of rescuing the second law to work, I said earlier, what needs to happen is that when you throw something into a black hole, the area goes up by enough to make up for the lost entropy. But it also means that if you first make a black hole from whatever, that whatever stuff that first made the black hole is going to be gone now. It's going to be inside the black hole. And so the entire area of the black hole that you made must be greater than the entropy that you destroyed when you made the black hole. And what at Hooft and Lenny, I think, we're thinking about is some sort of thought experiment where you might have some spherical region with some matter in the universe. And in their intuition, you could always convert that region to a black hole of the same size. So there's your region. It has 100 elephants in it. Now you cruelly kill them all by crushing some additional mass onto them. And you make a black hole that's as big as the sphere in which these elephants were floating to start with. Okay. So now, if you buy into this whole idea of the generalized second law that Bekenstein had invented, and there was a lot of evidence that it's probably true, that law would guarantee for you that the entropy of the elephants was less than the surface area of the black hole that you made. But then that would have had to be true whether or not you make the black hole, right? The entropy of the elephants had to be less than the area of some sphere that you can draw around them, right? And that was sort of the key idea, that the world is like a hologram in that sense, that you could have written all the information about the elephants onto a sphere that surrounds them at a certain limited density of zeros and ones. And that would describe completely what's in there, because that's what that implies. If the entropy of the elephants is less than the surface area in some fixed units called Planck units, that implies that in some sense all the information could have been stored on that surface that surrounds the elephants. And that's what led at Hooft, I think, he used the word hologram, I think, in that paper, that he just didn't put it in the title. And then Lenny, of course, put it in the title and elaborated on it. That's where that word came from. For when you have a hologram in the usual sense of the word, what that means is there's a two-dimensional surface that gives you the illusion of some three-dimensional object. The holograms that these guys were talking about are in some sense much more refined than that, because the everyday holograms, they really just convert a flat surface into a curved one. They don't tell, if you see some head of a person, they give you no information about what's inside the head and, what each atom in the brain is doing. Whereas at Hooft and Lenny's holograms were really 3 dimensions from 2, fully 3 dimensions. Everything is stored on a surface that can fully describe what's in the interior of that surface. And that's what they asserted, and they asserted this because they wanted it to be true that the black hole entropy really represents, I believe that's why they asserted, that it really represents a capacity for storing information. They didn't want the information to be lost, so they wanted to think of the information as residing in some sense on the horizon of a black hole. And that could only work if Bekenstein's generalized second law worked.
Well, I think that this is a really good time for us to shift to your work and how it has emerged from some of these concepts we've been discussing. And I think I know that you mentioned a little bit about your interest as a high school student in quantizing gravity, but for our listeners who are maybe not familiar with this whole problem of quantum gravity, I think it would be worth just glossing what it is, and then why for you it should not be thought of as a high energy problem, but a low energy problem.
Good. Yeah. Well, as to what the problem is, I would say it's a continuation of what, the role of physics in the history of science, I think, has been it's played many different roles, but one that's very close to my heart and that's closely connected to the invention of science as a method for discovery in the say around 1600 or so, is this idea of unification of phenomena, that we are able to describe more and more things with fewer and fewer ingredients. So the most dramatic example, I think, to this day of that was when Newton discovered a single law of gravitational attraction that explained both how the apple falls and how the planets move around the sun. It's hard maybe for us today to appreciate just how radical that was. This was at a time when people thought of the terrestrial and the celestial spheres as being fundamentally distinct things, and the mere notion that you could come up with laws that cross between them with no effort at all, and apply equally to both, was mind blowing. It was unbelievably radical revision of humans' picture of what the world even is. It broke through that barrier and it unified celestial and terrestrial phenomena. And a lot of the history of physics, at least the part that I always found particularly attractive, is sort of a story of sequences of these kinds of unifications. So, in the 19th century, Maxwell discovered that electricity and magnetism are like two sides of the same coin, and by describing them in a single framework, he discovered that light is electromagnetic waves. He discovered for the first time what light actually is. So that's another nice thing about unification, that once you have the new theory that can describe more things with fewer ingredients, it tends to give you entirely unexpected, radical new phenomena that you couldn't even have asked about beforehand. So you put electricity and magnetism together, you discover that there's a sort of self-reinforcing thing or propagating thing where they just keep on going, electrical and magnetic waves making each other, and you calculate how fast do these things move, and you find, they move at what we also know as the speed of light. It matches it. People already measure how fast light moves. So suddenly you realize, that's what light is. And then let's say, special relativity at the beginning of the 20th century was Einstein's way of reconciling Maxwell's theory with Newtonian mechanics. They didn't fit together because it didn't make sense to say that light had a particular fixed speed. If you can just go to a different reference frame, then it should be faster or slower. And so he threw out space-time structure as we knew it to make sure that it always has the same speed. Then he had to reconcile that with Newton's laws of gravity. He invented general relativity. This act of unification gave us totally new things. Now, the universe could be expanding. In fact, it is expanding. There's such thing as black holes. Let's go study them. So it both changes how we think about the world. Gravity is not even a force, but space and time are curved in ways that are dynamical. So this kind of stuff I always found absolutely amazing. The fact that it's sort of a combination of a lot of tedious, sometimes not intrinsically very interesting experiments and data, but hidden in those decimal places are evolutions that totally change how we think about the world and about what it is, and that but it's not some random thing. It's not something we just make up in an armchair. It's something that's forced on us by data. Quantum mechanics, of course, is an example where we're really dragged kicking and screaming to the theory. People took forever to accept it, I think some people still have difficulties with it. But yeah, it's a lot crazier than what anybody would have made up. But it's, it's forced on us. And that's the nice thing. It's not random, but it's really wild. So what's left now, in the very big scheme of things, what we haven't been able to put together in physics is this framework of quantum mechanics with Einstein's theory of gravity. And that is sort of the remaining task of unification. That's what we call quantum gravity, that thing that we're looking for. I think it's a beautiful problem. I don't think I could have articulated that. Well, certainly when I was a beginning graduate student, I wouldn't have been distinguishing very carefully between, for example, particle theory and quantum gravity. But pretty quickly, like in my first year at Cambridge, it became clear that I was far more interested in one than in the other. As cool as it was to think about elementary particles and maybe discover some new ones, but it resonated less with me. It seemed like it was more... Yeah, it didn't quite go to the heart of where the main challenges were in understanding the laws of nature.
And returning to the second part of what I asked you, why do you think it is maybe best, practically speaking, these are my words, not yours, to treat the unification of gravity and quantum mechanics, on the other hand, as a low energy versus a high energy problem?
Oh, I'm sorry, you already asked, and I forgot to comment on that. So, yeah, just for context, I should say, so usually people who are interested in quantum gravity have been traditionally considered to be part of the high energy physics community. And, that's great because there are a lot of really amazing physicists, and we get to say that there are colleagues who do high energy physics. But over time, so why did people think that way? Well, if you think like a high energy physicist, what you're thinking about is higher energies allow you to probe shorter distance scales. And that's why we build these big accelerators, so we can accelerate particles to higher energies. That effectively makes a better microscope. You get to see what's happening at shorter distance scales. The relation is inverse, so the distance scale you can probe is sort of inversely related to the energy you can get these particles to. That just comes out of the structure of quantum mechanics. It's the way quantum mechanics works. In that sort of mindset, you can ask, well, at which point is gravity even going to matter for me? Because, if you're a high energy physicist, gravity usually doesn't matter at all. Gravity matters for large objects where a lot of mass can sort of accumulate and then the masses can tug on each other. Gravity is in a sense a very weak force, in that if you ask, let's say for a hydrogen atom, what holds the proton and the electron together, there's an electric force that holds them together. It's many, 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 many times greater than the gravitational attraction between them. Okay. But of course, gravity will become important eventually when you concentrate a lot of energy in a small region, then maybe you can make a black hole. And so you can ask, well, how big does the energy at an accelerator have to be so that you probe that kind of distance? And the answer is, like a million billion times higher than any energies or something like that we currently probe accelerate, enormously higher. Okay, so in that sense, quantum gravity is a high energy problem, that if you crank up the energy in particle collisions by such a ridiculous factor, then eventually you're going to make tiny little black holes instead of new particles. Now, that is true. I don't doubt it. But it's not been a very fruitful way of making progress in quantum gravity. What has been much more fruitful is the kind of direction that began with Bekenstein's and Hawking's work in the 70s, where we ask, well, what do black holes do? Black holes do interesting things that become more interesting when they get bigger, because we have better control over the arguments. The fact that black holes radiate, that they seem to lose information and so on. The argument for that gets better when you consider bigger black holes than smaller ones, because the sort of corrections due to unknown quantum gravity theory effects become smaller, should become smaller, we think, in that limit. Then we learn about the holographic principle. We learn that gravity knows about its own quantum states, that it knows about the quantum states of matter. Things like my own discoveries, the covariant entropy bound and so on, teach us that there's a connection between geometry and information that's very universal and in some sense becomes more powerful at large distances than at small ones. If I tell you that the amount of information in some region of space is controlled by the area of the surface and not by the volume, one thing I've told you is that it's also much smaller than you might have thought. Normally we think that we can sort of put independent bits of information in each little cell of volume, and so the information should grow like the volume. In fact, I can only put as many zeros and ones as there are tiles that fit on the walls of the room. That's a lot less zeros and ones. And that discrepancy between how much information we naively might have thought is in the world and how much there really is in the world, that discrepancy becomes more and more drastic the bigger the regions are that we consider. So in that sense, I think most of the really interesting things we've learned about quantum gravity pertain to large distances. They become sharpest and most dramatic at large distances. They have nothing to do with trying to go to very high energies. And so it's in that sense that I think we're not studying a high energy problem. That's not where the key difficulty and the key sort of, and the fun is with the problem.
This raises a couple of very interesting questions. One is, you wrote or said elsewhere that you think that this is a way of treating quantum gravity with a bottom-up, old-fashioned bottom-up approach rather than a top-down approach. And I'm wondering just what exactly that means, how it connects to what you were just saying.
Maybe the way I would characterize it is that a lot of what in the past has led to progress in physics and to discovery of new theories and so on is that we see certain patterns in the data. Either just patterns that suggest a particular law, a particular rule that would explain why we see these patterns. In some cases, the patterns can seem like conspiracies or fine-tunings. So, why is it that all bodies fall at the same rate? I don't know if you've ever seen the hammer and the feather being dropped by an astronaut on the moon. You can really illustrate that once you take messy stuff like air resistance out of the equation, these things drop exactly the same rate. Why is gravity like that? We have a very similar theory, electrostatic repulsion and attraction, which has the same kinds of formulas in it, but each kind of particle or object gets its own charge. And so depending on the sign of that charge, it might be attracted or repulsed by another object. And in any case, the rate at which it moves depends on its mass and its charge. There are two parameters, and they can interplay in different ways. And charged particles don't all move in the same way. They move in very different ways. But gravitational charge seems to be exactly proportional to gravitational mass. And so the resistance to acceleration, the inertia, cancels out against the greater gravitational attraction. That's how it looks like in Newton's theory. So that's another example of a pattern that requires an explanation. And Einstein was able to give an explanation by saying, it's not a force at all. It's really all bodies just trying to go as straight as they can in a curved space-time. I think that the holographic entropy bounds that I discovered and generally these patterns of relations between the areas of surfaces, geometric aspects of space and time, on the one hand and the quantum information content of matter on the other, well, they are like these sort of very intriguing, but yet not fully understood, not really explained patterns. They seem conspiratorial for now. They don't, every time you check it and it works, it's a bit of a miracle. What we would like to have is an explanation that's analogous to Einstein explaining why all things fall at the same rate. Oh, in Einstein, it couldn't have been any other way. It was, space and time was just put together in such a way that, this was ensured from the start. And hopefully that way of understanding how space and time emerge will be amenable to, extending that into a full theory of quantum gravity. It's a sort of hint about the way that quantum theory and gravity fit together that is much too, it's a very broad pattern. It's been tested over and over. I don't think we can just say, it was an accident, it won't matter for anything. But we still don't have the deeper understanding of it. And I think that deeper understanding is going to be a quantum theory of gravity, and it should help us get to it. That's the hope. I think that's why it's significant.
Another thing that's very interesting about the approach that you were describing of treating quantum gravity as a low energy rather than a high energy problem is that it seems to be somewhat agnostic on the theory of quantum gravity from which you're approaching the issue. So you don't need to be committed to M theory or loop quantum gravity or causal set theory or anything like that. And what I'm wondering, though, is holography is best known from the ADS CFT correspondence, and that's, of course, very closely tied to M theory. So I didn't know that holography was a general feature of quantum gravity.
Yeah, that's an interesting point that you're making, a very good question. So far, in what I've said, I've used the word holographic principle and holography in a way that it would have been used 20 years ago, or 15, 20 years ago. 20, 25 years ago, I should say. And referring to patterns in the distribution of quantum information in space-time that we sort of recognize and find puzzling and find fascinating, and then try to sort of understand how to, first of all, describe them in a systematic way, and then maybe understand the deeper origin. Holography today is used mainly synonymous with something called the ADS CFT correspondence, which was discovered by Juan Maldacena in 1997. And that is a theory of quantum gravity. It's a complete theory of quantum gravity, unfortunately for spacetimes that are not like ours, but which nevertheless allow us to ask many deep and interesting questions. For example, in spacetimes that are ADS, anti-de Sitter, some shape of space and time that we don't happen to be living in, but in such a spacetime you can still make black holes and ask what happens when they evaporate. And Maldacena's theory tells us what happens, namely that no information is lost. So it's an incredibly powerful framework that immediately answers one of the most important questions that we can ask about quantum gravity. And because it's so powerful and it is a complete theory, it has been incredibly useful, not just in quantum gravity, but also in many other branches of physics. You can actually use gravity to learn something about strongly coupled quantum field theories and so on. In fact, most of the first few years of work on this correspondence went in that direction. And so it has really dominated the work of, probably tens of thousands of physicists over the last few decades. And because it followed shortly after Lenny's and Hoft's papers, And it did sort of realize this notion of holography in a specific context through a quantum gravity theory in which there sort of weren't more degrees of freedom to start with than what fits on the boundary of the space-time. It rightfully was called a holographic theory. And then since that's where 99% of the work was in the field, it eventually became just synonymous with holography. That's what. So that's fine. That's just a linguistic question. So now we're sort of in a situation where saying holography could be, well, for most physicists, I think it would. If you don't qualify it in any other way, then it would just refer to the ADS-CFT correspondence. That's not how I refer to it here. The way I would fit in the ADS-CFT correspondence is like it's more narrow in that it only pertains to a particular class of spacetimes, whereas the kind of ideas I talked about in the context of the holographic principle are completely general and work in our own universe as well. But it's also, the ADS-CFT correspondence is also much more complete. It's not just a pattern, a hint. It's the theory. For those spacetimes, that's it. It's a complete theory that describes what is going on. And so, and it's been incredibly valuable, not just because it told us that information comes out of black holes, but because in many other ways it can help us cross-check our ideas about quantum gravity more generally. And so it's been a very complex and fruitful back and forth between people asking about quantum gravity in spacetimes like the one we live in, and people more focused on exploring and understanding the ADS-CFT correspondence. I've certainly worked on both things extensively.
And you mentioned a few minutes ago something known as covariant entropy bounds. And are those Bousso bounds? Is that what they're...
So the Bousso bound, yeah, the name I gave it is covariant entropy bound because I guess you don't name it after yourself to start with. But a lot of people refer to it by my name, and it's basically a generalization of this statement that I made earlier, where I said, look, if you have these elephants sitting inside some imaginary sphere in the universe, and now I convert these elephants into a black hole with the same size, well, they couldn't have had more entropy than the area of that sphere that surrounded them, even if I don't convert them to a black hole. There's some relation between information content of a region and the surface area surrounding them. Well, that turns out to be false. It's false when you, for example, look at really large regions in our own expanding universe. It's false when you look at regions that are already deep inside a black hole. It's maybe in hindsight not surprising that it can be false because the argument clearly only works if the thing that you're starting from isn't already a black hole or in some other way it's very strongly gravitating. What I was able to do is write down a conjectured relation, a proposal for how areas, arbitrary areas in any situation are related to the quantum information of adjacent regions or regions that are enclosed in these areas. That relation appears to be completely robust, and it holds even inside black holes and in our expanding universe. But it's for the same reason, it's a little bit further. It's not something that would have followed just by thinking about, for example, Bekenstein's work and the generalized second law of thermodynamics and wanting those kind of things to work. That's how, of course, we were led to that next step. But it's much stronger than what would have been needed for the consistency of black hole thermodynamics. And it provides significant additional evidence that there is, an incredibly rich pattern in the connection between quantum information and space-time that we need to understand, that we need to get at the roots of.
Is there an intuitive way, maybe, of describing how the bound would be reached or discovered for some volume like this room?
Well, for a volume like this room, the bound really would just say, well, the entropy in this room cannot be larger than the surface area of the walls in certain units. Okay? In this room, we didn't need my bound all that much because this room is not very strongly gravitating. We're not about to form a black hole. We're not feeling the expansion of the universe on this distance scale and so on. But when you, for example, look at some star that's collapsing and it's it's burned out its fuel, it's collapsing, it's forming a black hole. Eventually, the star is entirely inside the event horizon that it has formed around it. But the surface area of the star keeps shrinking as the star is collapsing. Yet, the amount of information that's in the star can't have changed. And so sooner or later, it'll be true that the surface area of the star will be smaller than the amount of information contained in the star. At that point, the holographic principle in the way that was originally formulated by Hooft and Susskind would just not be true. Another example, which was noticed by Fischler and Susskind, so doing Susskind himself, is if you look at the universe on very large scales. The universe is spatially what we call flat. In other words, space is actually not all that curved. Okay, it's the same kind of space that we learn about in high school. You call Euclidean space. Okay, and galaxies are sort of, distributed at more or less even density, and each of these galaxies contains a certain amount of information, right? So that means that if I look at a really large ball of space, some interior of some large sphere, right, the amount of information is going to be proportional to the volume in that sphere. So the volume grows more rapidly than the area as I make the sphere larger. So I can find a sphere that's large enough that the information in it is bigger than the area. Right? I just look at a large enough sphere, and that's going to be the case. So these are simple examples of where the naive sort of holographic principle is just not true. And in fact, Fischler and Susskind pointed this out, and this is how I got dragged into the subject. I heard a talk by Willy Fischler that presented a proposal that they had come up with for fixing this issue. And the proposal had a number of difficulties, but one that I immediately recognized and apparently had not been pointed out before is this issue with a star inside the black hole, that it doesn't even work for the interiors of black holes. And so, to their credit, they didn't say, oh, you stupid little kid, and, we're very experienced people, and this might be a small deal. They said, oh, this sounds important. You should work on this. Our proposal is probably wrong. I thought that was just super cool, first of all. Lenny was not and other people had criticized their proposal for various different reasons, and that hadn't moved them. But for some reason, I said something that they thought was important. And so I was like, okay, you know what? I am going to.
That's great.
And I did. And Fischler was just visiting, but Lenny was very encouraging, and I eventually came up with the proposal I came up with, and that, yeah. So I felt I was very lucky that I was at Stanford at that time, being exposed to this question and hearing about it.
Well, for these last few minutes, I'd like to ask a bit about some of the work you've been doing recently, and then I just have a couple of orthogonal questions that I'm curious about. But I know you've been doing some work on quantum communication, and then gravity as quantum error-correcting code. And I'm just wondering what those two pieces of work are about.
Well, over the years, so right now I talked about something that happened like 25 years ago, right? Believe it or not, but more things have happened in the past 25 years. A lot of things have happened, and a lot of them were, of course, done by people younger than me. And they were helped greatly by having the ADS-CFT correspondence as a concrete setting where you can study a specific theory that actually is the quantum gravity theory and check that the ideas you have about how information and space-time work against what you know about that theory. So you can have a lot more confidence that your ideas are right, even if those ideas are perhaps more complex and more refined and a little bit otherwise would be harder to check. So one of the key things that we have learned, which I think we now understand fits into this actually very general scheme that applies to all spacetimes, not just ADS, but which was first understood by studying ADS, is this idea that the way that a gravitating spacetime encodes our local information into a quantum state is an example of something called a quantum error correcting code, something that people began studying also many years ago, which the significance of which I did not appreciate at the time. I thought it was maybe a bit of an engineering problem. When you build a quantum computer, those things are not perfect. They lose information sometimes, and you want to build in a kind of redundancy that protects against the loss of information to an environment that degrades your quantum information inside the quantum computer. You can't do that in the same way as you do it with classical information by just duplicating it, because quantum information cannot be cloned. But there are other ways of doing it that are more subtle and sophisticated. That ironically, John Prescott, who I mentioned earlier in the context of the holographic principle, was also a pioneer in that field. Well, in the 2010s, I believe, Daniel Harlow, I think Almeri, who I also mentioned before, and I think Aaron Wall played a role in this, Shidong, and others understood that in ADS-CFT, the way that the quantum information is encoded, that it is precisely a quantum error correcting code. That means that I can give you different parts of the boundary of the space-time, and if I give you 2/3 of the boundary, it doesn't matter which 2/3 I give you, you can reconstruct what's in the center of the space-time. But if I give you only 1/3, you have absolutely no idea. This is the kind of thing that happens in quantum error correcting codes. Over time, that relation was further refined. My colleague here, Jeff Pennington, and my former student, Chris Akers, pointed out that the way the information is encoded on the boundary is through... So in order for the information to end up on the boundary, you have to it's as if gravity was solving a particular quantum communication problem, where I'm trying to send you a message. I have certain resources available. The resources turn out to be proportional to the areas of space-time. And I can successfully send you the message if the message isn't too long. So I basically burn up these resources by sending you the message. So if I try to send you too much, I just don't have enough resources for that. The kind of problems that people usually like to consider, because we're lazy, are so-called asymptotic problems, where I make the problem a little bit simpler by imagining that there's like infinitely many of you and me, and each one is trying to send that message to the other. But we get to take advantage of certain ways of sort of compactifying. It's like creating a zip file or something on your computer. You can get rid of some redundancies and save resources by doing so. And the amount of resources that you then need is measured by something called the von Neumann entropy of the message that you're trying to send. Well, in the real world, it's rarely the case that there's infinitely many copies of you and me, and so we must solve what might be called a single-shot quantum communication problem, where I don't get to take advantage of this extra redundancy and being able to compactify and so on. And in that case, the amount of resources that I need to send you the same message is in general higher, and it's measured by something called the smooth max entropy that, in fact, to my knowledge, was only introduced into quantum information theory by Renner and others in the noughts of this millennium. And what my student Chris Akers and my colleague Jeff Pennington realized is that actually governs what region you can reconstruct from the boundary of ADS. So it's the areas have to be viewed as a resource, not for weighed against the von Neumann entropy of the quantum information in the matter that's in the universe, but this weird new thing called to me new, called the smooth max conditional entropies. Those are the things that enter. Okay, so this was to me another revelation that increasingly sophisticated concepts from quantum information theory enter into how space and time actually emerge, and it's things that I'm going to be honest here, that I would have dismissed as overly related to practical engineering problems. I was like, why is John Preskill working on quantum error correction? Like, who cares about errors? Those are practical issues. What a loss to our field, and now he's not working on black holes anymore. I'm so sad. Well, he was way ahead of the rest of us. And then single shot versus asymptotic quantum communication problems. One is the sort of idealized thing that you might think will enter into a quantum theory of gravity. The other might strike you as, a practical problem unlikely to show up in a fundamental theory of physics. Well, gravity thinks like an engineer. It's a wonderful, I think it's a wonderful story that we've been taught again and again, that these sort of very applied real-life almost concepts from quantum information theory are the ones that matter the most in our growing understanding of how space and time emerge. And so that's been a wonderful thing to be part of. Another, by the way, just to squeeze that in, is that gravity is so powerful, and its sort of hidden knowledge about quantum mechanics is so powerful that we've discovered new things about theories that have nothing to do with gravity naively, about quantum field theory, like the standard model of particle physics. We have, for the first time, a lower bound on the energy density of matter. Energy density of matter can be negative. So 0 is not a lower bound on it. Like, you can have some negative amount of energy in a small region of space. That's totally okay as long as there's positive energy elsewhere. But we never had an actual expression for how low it can go. We discovered such an expression by thinking about how gravity organizes quantum information. It's very easy to derive from a fairly simple conjecture about how that should work. And we got this very nice expression that has no gravitational constants in it. So it looks like it's purely a quantum field theory statement. And then people went and wrote down 100-page proofs in quantum field theory, using all of the powerful methods of algebraic quantum field theory that I didn't even know about, to show that this is really true. But I think it's extremely remarkable that gravity knows so much about quantum mechanics that we can effectively use it as a discovery tool about a theory in which naively we have far better control over, we completely understand, and so on. We still discover something new about it.
Everything you've just said is so fascinating to me, and I don't want to get into a critical exegesis of your language, but some of your language I found really interesting. You said that gravity knows its quantum states, it encodes its quantum states, it's solving a communication problem, a quantum communication problem, and so on. And what I find so interesting about this is that, particularly with regard to the literature around ADS-CFT, gravity and space and time in the bulk are thought to emerge from the boundary theory, so they're not thought of as being fundamental. They're kind of not playing an active role. They're a byproduct of what's going on the exterior. I spoke with Eric Verlinde about a year ago or so, and he doesn't even, I know this is a little bit different because we're getting back to black holes, but he doesn't even think of the interior of black holes as being real. He just thinks what's real is the exterior. And so it seemed like you have a somewhat different appraisal of the situation, or maybe I'm just reading into your language a little bit too literally.
I guess what I won't get into is the question of whether something is real. I think that's never been a fruitful question in science. The question is, what is an efficient description of our data? But what we can ask is, to what extent do we think some property is emergent as opposed to fundamental? So, for example, the conductivity of a metal, I think we would say that's an emergent property. You have to have a lot of atoms before it makes sense to define that property. But in that limit where you have infinitely many atoms or molecules, that property now becomes a well-defined object. But you wouldn't expect it to show up in the fundamental description of nature. Space and time clearly seem to have that property, that they're emergent in a certain sense. So the case where we know how to make this most precise is, again, in the ADS-CFT correspondence setting, where we have a specific theory, and that theory has some dials. I can dial how many degrees of freedom I have in the theory. And as I dial that number down, the interpretation in terms of the space-time disappears. So if that number is large, then the theory on the boundary, this conformal field theory, is always the fundamental theory. It's always the one that I can ask all of the questions, and that will get them right. But when the number of degrees of freedom are large, then there exists a good approximate description that I would describe as a gravitating space-time. And it's in that sense that we think of this as being a quantum theory of gravity. It contains that limit of a classical theory of gravity in it. If I turn the dial so that the number of degrees of freedom becomes small, then that alternative classical gravity theory just becomes completely inaccurate. It's not a good description at all. And so in that sense, I can make space-time appear or disappear by turning that dial, right? So in that, it's clear that it's not, I can really interpolate between situations where space-time is a good description and space-time where it's just not at all a useful description. I think that is clear. What we've also learned, especially in recent years, is that much of this structure that we understood through the lens of ADS-CFT is actually far more general. The idea that gravity is like a quantum error correcting code, that there's a certain sense in which you can recover larger regions from more boundary-like smaller ones. That's something that in recent years, for example, Jeff Pennington and I have made that very precise. That seems to work in arbitrary spacetimes. It's not tied to ADS, even though that's the context in which it was first discovered. So that makes me optimistic that these, this is like the two senses in which holography is used, right? There's this sort of original, very broad set of ideas, information and geometry are somehow tied together. And then there's the ADS-CFT correspondence, which was a beautiful, complete theory in which you could study things in far more detail. But on this original sort of side, that side has become much richer, thanks in part to interactions with this ADS-CFT correspondence. It's not just, my entropy bound that lives on that side. It's also the notion that the way the information is encoded is quantum error correcting, that it uses these funny single-shot quantum communication protocols, and so on. All of that stuff is actually quite general, and it leaves me optimistic that we will be able to go beyond ADS-CFT and understand how quantum gravity works in the real world.
Well, the absolute last thing I wanted to ask you about today is you mentioned fine-tunings a bit earlier in our conversation. I know that this is wholly unrelated to what we've been discussing, but do you still find yourself thinking that string theory or something that will come from string theory is not only going to be the right theory of quantum gravity, but that it will solve these fine-tuning problems?
I do. I think that first of all, string theory is sort of we were talking earlier about old-fashioned ways of doing physics and bottom-up and so on, and I like the fact that what we talked about most of the time today is it didn't require me to commit to any particular, still hypothetical theory about what quantum gravity should actually be, because it protects me from, maybe potentially wasting my time if I work on something that ends up having nothing to do with reality, right? That said, I find it extremely difficult to imagine that string theory is not in some way connected to the correct quantum gravity theory for our universe. What makes it difficult is that the connection might be quite hard to trace. It's very hard to start. The analogy that I like to give is, we have the standard model of particle physics, which describes every experiment we've ever done outside of, cosmology and gravity, right? And I think there'd be very few people who would argue that what goes on inside a zebra, for example, is in some way in violation of the standard model of particle physics. But that does not mean that we know how to explain the behavior of a zebra, starting from the laws of the standard, the Lagrangian or whatever, the equations that we have for the standard model of particle physics. It's too far removed, and it's much more complex. It's so many layers and levels away from where the theory is simple. And so we need effective descriptions, and that's why we have zoology and whatever, behavioral science, and we can't bridge that gap. But that doesn't mean we think that the standard model of particle physics is wrong. It's just not. Yeah, it's too far removed. String theory might be simple at energy scales that I discussed earlier, where you'd have to go like 1 million billion times higher than current accelerators, but we can't test it at those scales. And so then to connect the fundamental equations to what we actually see today at the low energies that we can access, well, that's very hard to do, especially if you don't understand the theory completely as we do. And I think we don't understand string theory completely. That said, there are some hints, I think, that string theory has the right ingredients to explain some of the phenomenology that puzzles us about our universe. One of the things that puzzles us, the universe is very old and very big compared to what you naively would expect if you do some estimates using the best particle theory that we have, the standard model. You can calculate how much energy density empty space should have, and it turns out it should be like many orders of magnitude more than it actually has. So you have to explain why it has so little. So Joe Polchinski and I proposed an explanation of that in 2000, which has come to be known as the string landscape. Thanks again to Leonard Susskind, who was very good at naming things. And it's based on the idea that in a theory, it used to be considered an embarrassment a bit of string theory that it likes to live in 10 or 11 dimensions, like 9 or 10 spatial dimensions plus time. And so you have to posit that some of these dimensions are sort of curled up in very tiny circles or other shapes so that we would not have seen them. And it seems to us like we have only 3 spatial dimensions. But what Joe and I pointed out is that if that's indeed how things work, there arguably are an extremely large number of possibilities of how you could curl them up. This is not because the theory is complicated. It's the same statement as saying that in the standard model of particle physics, which is a relatively simple theory, it has a certain countable number of ingredients, well, it has a lot of solutions. If I move one electron from this side of the nose to that side, it's already a different solution, completely orthogonal quantum state. And then just look at the larger world. To say there would be 10 to the 500, no, that would be a vast underestimate. Right? Well, we argue that there are at least 10 to the 500 different solutions to how you would curl up these extra dimensions. And that was helpful for explaining why the universe could be so large and old, because in some of those combinations, it would be inevitable that some of them just have very little vacuum energy, as we show. So then the universe could effectively create different regions. I mean, this is something you don't just say; you show that it happens dynamically, where the vacuum energy takes on different values, and then some of them will last for a long time and become very big. So this type of argument in its most general form wouldn't have needed string theory, but we were sort of, it was kind of string theory that rubbed our nose in it. That theory gives you those, many ways. You could imagine maybe there's some other theory that has extra dimensions and many ways of going down to 3 spatial dimensions. And from the point of view of our argument, that would be just as good. But I find it remarkable that in string theory, you're just handed the ingredients that you needed to solve this problem. So I think that's one very significant reason to take the theory seriously. There's currently, to my knowledge, no alternative explanation of this. Is called the cosmological constant problem, and this is the only solution that right now is out there. That doesn't prove it's the right one, but I think it's interesting that in more than 50 years of worrying about this problem, I don't think we have another one. Another reason that I think string theory is, continues to be studied, so carefully and extensively is that it has, it's turned out to be a very powerful tool for making discoveries in mathematics. This interplay, of course, between physics and mathematics is very old and have been driving each other for a long time. But today, I think, in the last couple of decades, it's really evolved to a new level where entirely different fields of mathematics have been connected through arguments that ultimately came out of studying something called dualities of string theory.
Raphael, it has been such a privilege to come here and talk to you, and you are really a really gifted scientific communicator, so I hope you do a lot more of these going forward.
Well, thank you for doing this and for making science available to others. So I'm actually very grateful for that. Thanks.